In this video, we're going to introduce magnetic fields, and we're going to talk about the link between magnetic fields and gang signs. These are the learning outcomes for today's lesson, such as magnetic fields, current carrying conductors, magnetic field lines, magnitude and field strength of a magnetic field, and using the formula for it. So some background about magnetic fields. We've known about them for a long time. We've used compasses for as early as 200 BC. And a long time ago, we used to use lodestones, which always pointed in the same direction. We later discovered that this was the North Pole of Earth, but these were previously used as navigational tools. It wasn't until about 2 centuries ago that it was discovered that magnetism was actually connected to the electricity. We found out that all electric currents generated magnetic fields. We also discovered that an electric current has a magnetic field associated with it, and that all electric charges that are moving create magnetic fields. This magnetic field is separate from and in addition to the electric field associated with these charges. Stationary charges have no magnetic field associated with them, only their electric field. A magnetic field is a vector. It is represented as the influence around the magnet, and it should be defined in terms of its magnitude and its direction. When we talk about its influence, it's what it does to things around it and what things around it do to it. So it's that action at a distance sort of thing that we talked about earlier. In terms of the direction, it's easy to say the direction of the field goes from north to south. But if we consider that a magnetic field can be created by an electric field, how do we define its direction then when there's no physical north or south pole that we can see? The field lines are actually a line of force. So this means that the direction of the field line is the direction of the force on an object. If we look at a gravitational case, the field line direction at any point is the same as the direction of the force on a mass placed at that point. So when we talk about the force of gravity or the weight force, that's just a mass placed in a gravitational force, and that weight acts in the direction of the gravitational field lines, which are centrally or radially inwards towards the center of the Earth. Then when we go to the electric case, we take an electric field. Those field lines are the direction of the force on a charge placed at that point. In magnetic field case, it's the direction of the force on the north pole of a magnetic dipole that's placed at that point. So all three cases have this strong similarity that it's the force and the direction of the force on an object. Just in gravitational case, it's a mass. In electric case, it's a charge. And in magnetic case, it's the north pole of a magnetic dipole. A dipole is an object just with two poles. So when we say a simple bar magnet or a compass needle, these are examples of dipoles. It has a north and a south. If we want to investigate the direction of the field, we would place a small compass needle within that field. The needle will align itself to the field, with north following the field line direction. The strength of a magnetic field is represented by the number of field lines crossing a unit area, and this is perpendicular to the field. For a weak magnetic field, we would have very few lines, and for a strong field, we would have more lines, exactly like in electric field cases. The unit of the magnetic field is the Tesla. So when we talk about a field strength, we would say it has like 3 Tesla, 300 Tesla, etc. That is the unit. And the symbol for the magnetic field is this capital B with a vector symbol. Note that a magnetic field line forms closed loops through the air and through the conductors, unlike the electric fields that start and finish on the surface of the charged conductors. So the magnetic field forms this closed loop through air and through a conductor. And we had no electric field within a conductor. If we look at some bar magnets for interest, if we put multiple bar magnets together in sort of a variety of different configurations, this is what the magnetic fields would look like. So in this case, if we put the like poles, the north and the north together, they are repelling each other, so it's bending the magnetic fields further away than what they would ordinarily do. If we go a north and a south, unlike poles are attracted, and the field goes from north to south, so it creates a mini loop between the gap there. If we put them side by side, we create this sort of vortex effect. The north is then rotating down towards the south, and the north is rotating towards the south. And if we flip them so that the norths and the souths are aligned, they push each other away. So it bends away from the two norths that are repelled by each other, and it comes in and then pulls into each side of the souths. But again, there is no field directing between the two. They're pushing apart. So it's very similar to that like charges. The like norths repel and the like souths repel, but a north and a south are attracted, but it's attracted in one direction. It's not a mutual attraction there, so to speak. When we go back to Earth's magnetic field in this compass situation, we know that the direction is from the South Pole to the North Pole. That is the direction of the magnetic field. But remember that the direction of a magnetic field at any point is the direction of the force on the North Pole of a compass needle placed at that point. If we look at a compass needle near the surface of the Earth, it points towards the North Pole. The North Pole of a compass needle and the North Pole of the Earth must be different things then. The North Pole of a compass needle is that pole which points to the North Pole of the Earth. Thus, the North Pole of the Earth is attracted to the North Pole of the compass needle, which tells us that it is effectively the South Pole of the Earth's magnetic field. In other words, our North Pole is actually magnetic south. In 1819, Hans Christian Ørsted, a Danish physicist, showed that a current-carrying conductor produced a magnetic field. We can make magnets and magnetic fields with charges and current now. A really important definition to note here is that moving charges will produce both electric and magnetic fields. However, a stationary charge will only produce an electric field. The magnetic field surrounding a straight current-carrying conductor can be represented using magnetic field lines that form concentric circles around the conductor. The magnetic field lines become further apart, which tells us that it's a weaker magnetic field, and they become further apart as the distance from the conductor increases. You can see this picture here represents that. We've got a current-carrying conductor coming up, and you can see this magnetic field representation looping around the conductor. If we reverse the current so that it went downwards into the page, or downwards as we see it, then the direction of the magnetic field is now in the opposite direction to what it was. So it's flipped the magnetic field. There is a simple way to figure out the direction of the magnetic field around a current-carrying conductor, and it uses your hand, specifically your right hand. This is where the right hand rule comes in. The right hand rule uses your thumb to point in the direction of the current, and your fingers to wrap around the object showing the direction of the magnetic field. So if we have our current-carrying conductor pointing up, and we wrap our fingers around it, the rotation and curl of our fingers is actually giving us the direction of the magnetic field. And this is the right-hand rule. This is one version of the right-hand rule. Sometimes this is called the right-hand curl rule, because our fingers are curling around the page, or around the conductor, but it is another version of the right-hand rule. Have a go at this. Using the right-hand rule, with our two different conductors here, which of these is possible and which is not? So use the right-hand rule to place your thumb in the direction of the current and see which way the magnetic field should be rotating. Hopefully, you worked out that that one is incorrect. The right-hand rule does not give you a magnetic field moving in that direction. Some basic conventions. Think of current as an arrow. If an arrow was coming out of the page towards you, the first thing you would see is the point tip of it. So it would look a bit like this. You'd see like the small hole coming through the paper. If, however, the arrow was going into the page, you would see the back of the arrow. You would see the feathers as they're moving away from you. So it might look something like this in a bird's eye view. We use this convention to note and show the direction of the current when we draw fields. So the circle with the dot is coming out of the page, and the circle with the cross is going into the page. Using this information, of the two pictures below, which of these is possible using the right-hand rule and this notation to signify the direction of the current? Hopefully you identified that the right-hand side is incorrect. If we use our right-hand rule, the notation tells us that this is coming out of the page towards us or out of the screen, and then our fingers would curl around the object to signify that magnetic field or that field line direction, which is going counterclockwise as we look at the screen. Now if we look at a magnetic field on a current loop, first consider a loop of wire which a current flows around. We grasp the loop of wire with our thumb in the direction of the current, and our curled fingers indicate the direction of the field. So we can still use this right-hand rule, but now this is an application of that right-hand curl rule. So Our thumb points in the direction of the current, our fingers curl around the loop, and we've got the direction of the magnetic field. As we move our hand around, the loop direction continues. So you can see no matter where you are on this loop, your fingers are curling towards the left, and we would say this is the south. The field through the loop is approximately uniform. Magnetic field lines inside the loop are closer together than the magnetic field lines outside the loop. This indicates that the magnetic field in the loop is stronger than the magnetic field out of the loop. There are a variety of visual applications for the same thing. These pictures here show some different examples. So we've all just got current carrying loops in each case. They show the direction of the current, and it's a visualization of this is kind of using the right hand rule or the curl rule at each point. You can see that it's constantly rotating inwards and into the page. Here we've got our loop 90 degrees to us, and you can see the direction of the loops at this plane. Here we've used the vertical notation, so we can see the X's are going into the page, dots are coming out of the page, and the current is flowing in this direction. And here we've got our big magnet catcher looking thing with our dotted lines to show the magnetic field. From here, have a look at the workbook questions. Page 172 is the start of this, and there is question 1 to 6, which are relevant to these magnetic field lines and drawing the magnetic fields of a current loop. Ignore the solenoid question, as we'll cover that in the next lesson.